The first one's by Victoria Kostina of Caltech about the minimum number of fields to stabilize the linear system.
Thanks,
Victoria?
Steven. Okay, so this talk is going to be about information theoretic trade-offs in control. And the scenario we're considering here is the following. Suppose we want to control a system over a rate-constrained link, such as a wireless communication channel. For example, if you're a person who is standing on the ground and trying to control a flying drone, then it really matters how many bits you are sending over this channel, because it's a rate-limited link. Or you can envision a scenario where you have two systems talking to each other, again over wireless. So it's rate constraint again, and trying to coordinate their actions and make decisions with this limited communication. And I'm going to, for the most of the talk, I'm going to be focusing on the linear system, linear scalar system. So this is a toy example. So here we have a system state X, which evolves according to this linear equation. And everything here is scalar. Vi is the disturbance, which is modeled as random noise, which can be potentially unbounded. And Ui here is the control action. The goal here is to bring the state as close to 0 as possible. Okay. And A here is a known system parameter, which is known as system gain.
Just move the mic to the other side.
Oh, okay. Yeah, so A here is a system gain, which is a known scalar. And yeah, and we also assume that we know the distribution of the noise. And just for now, we assume that noise is IID. Okay, so IID, and they are analog, so they have some density. So that's, but they are identically and independently distributed. Okay, so here is the setting. So this is our system, which evolves according to this linear equation that I showed earlier. And the encoder here observes the state, which is then used to form a code word, which is transformed to the transmitted to the controller over this channel. And the controller chooses a control action U based on all the information it had received up to that point. Okay, so what we would like to do, the holy grail here, is to choose the encoding sequence, so to design this encoder and to design the controller, which means that we want to choose both of these sequences so as to minimize the cost, which is, in this case, the mean square error cost. Right, so we want to bring this state to the target location, and without loss of generality here, we assume that target location is 0. Right, so we want to bring it to 0, and the quality of our control is measured by this mean square error cost function. And the important thing here to note is that this encoding and control sequences, we do not impose any restrictions on them, apart from them being causal. So they cannot look in the future, but they can freely use all the information from the past. Okay, and channel and system here are given, whereas encoder and controller is what we can design for this given channel and for this given system. And yeah, as I said, I'm going to be mostly talking about this scalar model, but all the results actually easily generalize to vector case, which is more relevant for practice. Right? So for vector case, we have everything vector here, and A becomes a matrix, and we can also have a cost function which is called linear quadratic regulator, So you can think of it this way. So imagine that X contains not only the location coordinates, but also, let's say, acceleration and velocities. And perhaps we want to bring the location to 0, but we don't want to do it with very high acceleration or with very high velocity. And so we have different constraints on those different coordinates, and this can be captured by this Q matrix. And then similarly, we can also have a cost on this U to save energy. And so we want to penalize larger control actions. So this is standard setting called linear quadratic Gaussian control. So usually people look at Gaussian VIs, although here we do not put that restriction. There's been a lot of prior work in this area, so it's a relatively well-researched area. However, some very basic questions are left open, and this is actually what attracted me to this area. So this is quite significant research effort. However, these are all difficult questions, so it's a lot of things are left unanswered. And okay, so what we are after here is we would like to characterize this curve. So this is a cost that we can achieve versus channel quality. So channel quality, in this talk, actually, I'm going to be focusing on noiseless channels. So channel quality in that scenario would be just rate. So the transmission rate over this noiseless channel, or noiseless channel capacity. So data rate, number of bits per second that you are transmitting. And so we expect this curve to look something like this. And right, so as the channel quality deteriorates, the cost, the minimum achievable cost increases, and vice versa. And also there are two interesting asymptotes. So the vertical one, which is the standard control setting without rate constraints, and the horizontal asymptote, which is the minimum channel quality to guarantee stability, so to guarantee any bounded cost. And actually, in this talk, I'm going to be mostly talking about this asymptote. Okay, so let me try to explain why this is a difficult problem. So this is a problem which lies at the intersection of information theory and control, right? Because we are talking about control over a communication channel, and it seems natural that to solve this, we would want to bring together tools from information theory and control. However, traditionally, these two fields evolved for different settings. Right? So in a typical information theory problem, we would encounter stationary and memoryless sources and channels, whereas in control, our sources, so for example, the linear system that you saw, it actually has infinite memory about the past. So there is no memorylessness there. Also in information theory, we usually have block coding, so we can afford to wait for, let's say, 1,000 bits and then encode those bits. Whereas in control, it's really important that we have short delays. So we cannot have this luxury of waiting and introducing this coding delay because this system, so we have this system right here, and this A is, in a stable system, this A is going to be greater than 1, so it's a non-stationary process. So if we make it just be uncontrolled, so if we put U to 0, then it's gonna blow up. So we don't want this to happen. So we don't want to delay the system in order to allow ourselves to code. So what we want to do here then is something like convolutional coding, where we constantly outputting bits, whereas taking advantage of past memory. And I already said these delays are really catastrophic in this setting. And and final point is that in information theory, the data is usually static, so this is something given to you by nature. And the encoder just takes that object and manipulates it in order to transmit it over the channel, whereas in control, because we have this feedback loop, effectively the encoder modifies the data at future time instances.
Question?
Sure.
So in communications, in the control world, and of course stability is a major issue. Is there a course at this level of analog? Is there a correspondent to stability?
Correspondence to stability in
On the information theory side.
information theory side. It's a good question. Well, the basic assumption in information theory is that everything is stationary. We mostly care about stationary sources. So, yeah, no, I guess that's one of the issues why it's difficult to bring them together. Other questions? Okay, so the question I'm going to be focusing on for the most of this talk is actually really simple. So we have this scalar system, and here A is between 1 and 2, and we can only transmit 1 bit per channel use here. And it's a noiseless channel, so here the bits are labeled plus and minus. It really doesn't matter how you label them. So you only transmit one of the 2 possibilities. And the question is, can we achieve bounded cost with this 1 bit? So at each time instance, you transmit 1 bit. So very, very, very simple question. It's kind of surprising that it hasn't been completely answered.
Sorry, can we just one?
Sure.
So your state may evolve in the reals.
Yes.
But your feedback is of the bang, I mean like plus minus 1 type.
Yeah. So this system is discrete time sampled system, which values are real values exactly. And what we want to design a controller which takes as its informational input only one of these 2 values. Yeah, exactly. Yeah, that's exactly what we want.
So, I don't recall, but could you say something about how this relates to the question that Ananta had asked? So he was also worrying about mean squares.
Yes.
Could you say something about why he did not answer this question?
Well, there's been a lot of work in this direction. However, actually, I'm going to talk about it later. So the achievability schemes here use variable lengths. So they allow to send more bits at some time instances and fewer bits at other time instances. Then it's much easier to show an achievability result. So here, what we're asking is, what if we don't have this luxury? What if we always send 1 bit per channel? So that's one of the big sure.
This expectation is with regard to the stochasticity in the VI, is that correct?
Yes, exactly. So here we assume that X naught also, the initial state, has some probability density as well, and VIs also have probability density.
And those are given to us ahead of time?
The densities we know, yes. Yeah. Yeah, so exactly. So this mean square error is a function. The expected mean square error is a function of your control strategy, like of your UT.
So your UT can depend on the feedback of all the past feedback, not just the current.
Exactly, yeah. So that's a very important point. So we do not put any restrictions on this controller or encoder. So we allow full usage of memory of the past. And actually, this is very essential here. That this control, I'm going to show you the scheme that it leverages the memory.
Does anything change if you have a channel between the controller and the system?
Oh, it changes very much. Yeah, it's a completely different problem. It becomes a completely different problem, much more complicated. I was going to say a few words at the end about it. Yeah. Okay. So formally, we can introduce this fundamental limit. So m star is the minimum m such that exists a causal quantizer controller, which has m levels, and achieves bounded cost in terms of beta moment. And so this is the result. So if VIs are independent, so they have bounded alpha moments, then for any beta less than alpha, the minimum number of quantization points to achieve beta moment stability is floor of a plus 1. So if we particularize it to our case, so if you have a stable system, so a is less than 1, then this is not interesting, so we can get away with sending no information at all. Right? M equals 1, it corresponds to 0 bits. If a is between 1 and 2, then m is 2, which means 1 bit, and so forth.
So how does this relate to work arbitrage?
I'm going to talk about that. Yeah, they looked at bounded disturbances. Again, that's another important distinction.
Can you go back to the previous slide?
Sure.
So it's interesting that you don't have any distributional assumption except that.
Yeah, the boundedness of moments is the only thing we need actually for this achievability. So for converse, it's interesting. For converse, we need existence of density. If VIs do not have density, then you can actually do better than this. But for achievability, we don't need any further assumptions.
Beta is constrained to be already less than the highest moment of VI.
Sorry?
Beta is already constrained to be less than alpha.
Yeah, so alpha is we assume that VIs have density actually here we don't assume density. We assume that VIs have bounded alpha moment.
Then I agree. I'm saying if suppose alpha was 2, that is VIs have bounded second moment.
Yes.
Then A becomes maybe less relevant because beta is already supposed to be.
So if alpha is second, is 2, then what we are talking about is stability in terms of any moment that is slightly less than 2. So beta is like alpha minus small epsilon.
So this
the result is right. Sorry, the result is right, but suggests that time-varying strategies might be better than time-invariant strategy.
Oh, it's not only better; it's the only possibility. Yeah, I was gonna.
Assuming time-varying strategies ain't relevant. What I was noticing is that if you take something like a squared or a cubed or something, right, the floor sort of behaves differently than just the log. So you might get some benefits from trying to group symbols together.
Oh, trying to group symbols together. Yeah. So this corresponds to variable length. Indeed, it's easier. Yeah. So this is what previous schemes did in this direction.
No, I mean it could be like a fixed grouping.
Okay.
But because you're taking a floor, you somehow might get improvements over treating it.
Oh, like you mean like small time sharing? Yeah, you could do that. Yes, you could do that. Absolutely. Yeah. Sure.
What does M-level causal mean in this setting?
What causality means?
The M-level causality, yeah.
Oh, yeah. So M-level causality. Yes. So this is just a more general case of this setting where so we were looking at a controller and encoder. So in this case, it's only 1 bit, but in that case, it can be like log m bits. But causality just means that we choose these mappings based on infinite memory of the past, but we cannot look in the future. Okay, so let me tell you what's known about this problem, because as I said, it's been quite extensively studied. So the very basic case is bounded disturbances. So if VIs are bounded almost surely by some constant, then actually it's a very easy problem that has been solved. And the minimum m required for stability is indeed what we said it should be. The strategy is very simple, time invariant. I'm going to show you it to you in a second. So first, I'd like to show you this. So what if we don't have any rate constraints? So it's this infinite capacity channel. We can transmit reals over it. Then let's just look here. So what we want to bring this x to 0. So what is the best control action that you can choose? Well, the best one you can choose is actually to cancel what you observed. And that is going to result in a minimum mean square error cost equal to the variance of your noise, your additive noise. And so this corresponds to this vertical asymptote. Okay, so let's just remember this. So this is the optimal control when we do not have any rate constraints. Okay, and this is the scheme, the easy time invariant scheme, which achieves the limit for bounded disturbances. So we are looking at an unstable system here and bounded noise, and the scheme does the following. So here we are going to pretend the controller is going to pretend that whatever it observes it's actually the true state, and this has a name. It's called certainty equivalence control. Right, so xi hat here is a quantized version, so we just cancel the quantized version as if it was the true one. And then you can, and so what you do here is you have this uncertainty interval, and you have m level quantizer, so you divide it into m levels, and so you can compute, and so if xi was in less than ci, then with this control, the next state is going to be in this region. And then if we just look at this ratio, then it's really easy to see that that in order to make this thing decrease, you need the m to be greater than a, right? To make it go to 0, and otherwise it's going to diverge. Otherwise, the sequence is going to diverge, and then so from here immediately we obtain the m star. Yeah, and you cannot do any better than this. This is also a really easy, like, volume division argument. Sure.
Does this have to be, the control has to be minus a xi? It could be any k, as long as it stabilizes the. It could be. It doesn't have to be axi. It could be any k xi.
It could be anything. So this is an achievability scheme. So we are saying this control achieves the best we can do.
I see. Okay.
Yeah. Yes. Yeah. So actually, this is also a difference with how control people usually think about problems, because in control community, people usually look at the optimal strategy, and then they study the properties of that optimal strategy. So here we are taking an information theoretic approach, which is to say we're going to look at achievability, and we're going to look at converse, and then we're going to try to prove that those are close together or coincide in some cases. Yeah. So here, I'm going to talk more about that if I have time. Okay, yeah, so this establishes, so this argument establishes this asymptote for the bounded case. Right, so the idea there is that we need to divide that uncertainty interval into sufficiently many quantization points so as to beat this multiplicative growth of the system. And so now I would like to talk about unbounded disturbances, because this is where the problem becomes fundamentally different from what is known. So here, so imagine we now have a PDF which has tails, like an unbounded, and assume that we just try to do the same thing we did before. So just run the same quantizer that we did before. So choose two representation levels. Just if the system state is in this area, you apply this control, and if it's negative, you apply that control. Okay, so just trying to do the same time invariant strategy. Unfortunately, it's going to fail. Why? Because eventually, since your noise is unbounded, with probability 1, because we remember we are running this system for a very long time. Eventually, with probability 1, you're going to encounter a noise realization which is going to be outside of your conjectured bounds, and so from that point on, your system is going to run out of control. So actually, there is a result which says if you have unbounded disturbances, then you cannot use time invariant quantizers. So any time invariant quantizer with finitely many levels cannot achieve bounded cost. And so the only option, it seems like, is a zooming type quantizer, which was introduced by Brockett and Liberson. And so we use this zooming idea. So what it does is that we test whether we stay within the bounds, and then we zoom out. And so it's an adaptive strategy. I'm going to show you the strategy. Sure.
Previous also idea fails if x0 is not 0, right? If you don't know anything about x0, you also need some adaptation.
If x0 is unbounded density, yes. Yeah.
So then potentially, yeah.
Okay, so this is a reminder about our problem. I'm going to show you how we stabilize it with 1 bit. So this is the overview. It's a time variant. The encoder is a time variant thresholding rule. So the threshold actually has to. It seems like we need to vary the threshold with time, and then the controller uses the following strategy. So here CI is. This interval is the estimated interval containing xi. Okay, so this is something that the controller computes into conjectures. So it pretends, it acts as if xi was indeed contained in that interval. And then this sign I is the estimated sign of xi. So effectively, if you remember the strategy for the bounded case, so this does exactly that. So if xi was bounded by ci, then this is exactly the same strategy as in the bounded case. And of course, the problem here is the issue here is to devise a strategy of updating these CIs. So this is what we do, and actually sign we. It's either +1, -1, and we also allow 0. So it's 0 and we cannot say much about the sign. Okay, so we want to decide. So effectively, deciding the CI is everything. What we want to do, we want to look at the past and to make a decision about what is the likely CI, what's the likely interval, uncertainty interval where X lives. So this is a strategy. It's a scheduled strategy. So what we do, we choose K, and for K moves, we just pretend that we are in the bounded case. So this is called normal or zoom in mode, where we just operate as if the noise was bounded. Then for one time step, this is the probe time step, where we test whether our conjectures were indeed true. Right? So and most of the time it's going to be correct, but sometimes we're going to find that the noise actually produced a large realization, and so we are outside of our desired bounds. And in that case, we're going to enter this time-varying emergency or zoom-out mode. So this is a random stopping time. Actually, it's not a fixed constant. So K here is fixed. K is something we choose beforehand, but tau is something that is decided in real time. Okay, so in normal mode, as I already said, we just pretend that the noises are bounded, and the encoder in this case, the threshold is just 0, so we just output the sign of xi. So this is our threshold. We output plus if it's greater than 0, and we output minus if it's less than 0. Okay, I forgot to say the noise here is 0 mean. Okay, if it's not 0 mean, it's you just shift everything. So yeah, this is the threshold rule in this case. And the encoder just outputs the sign, and the controller acts as in the bounded case. So this is, so we pretend that xi lives within Ci. We divide it in 2 quantization bins, and we output either this value or that value, depending on the sign.
Sequence of CIs is predetermined until you hit the probe.
It's predetermined once you know C1, right? Where you start, it's predetermined, exactly. It follows this formula.
And then you change it and then zoom out.
And then it becomes random when you enter the emergency mode, yeah. Yeah, exactly. So here it's predetermined. So here everything is predetermined, and most of the time this is going to be the case. So most of the time we're going to be operating in this normal mode as if everything was bounded, and just sometimes we're going to be entering this red emergency area. Okay, so this is the probe. So after those k normal steps, what we are going to do, we are going to test whether the xi is actually staying within desired bounds. So here we computed the CIs according to this predetermined sequence. And here, since it's always a non-zero probability that the noise is larger than what we expected, we're just going to test whether xi is within this bound. So the quantizer here looks like this. So this is your CK. So you output plus if you are in this region, and you output minus if you're outside. And of course, the important part here is that it's a schedule, right? So both encoder and controller know where they are. So at this point, the controller knows that we are in the probing mode, so it knows how to interpret this plus or minus. And actually, the encoder at this time step, it doesn't do anything. It just applies an all-zero control. So we effectively use this information only to decide what to do next. So if the test came back as passed, then the round ends and we just start over. But otherwise, so if it's outside of our desired bounds, then we enter emergency mode. And again, both encoder and controller agree on this. So this is the emergency mode. So here, what we do, we repeatedly perform more tests. So the tests look like this, whether you are staying in this region, and we increase. So here P is some constant, which is again chosen beforehand. And we pick this P beforehand, and then we just exponentially increase the size of this interval. And eventually you're going to catch the state. Eventually the test is going to be passed. And when that happens, you just go back to the normal mode and you start over. Yes?
Could you just repeat, for the normal mode, the update equation for C involved B? Could you just remind me
this
what
one?
B is?
Oh, B here is the conjectured bound on VI. So it's a parameter which is set before.
So everyone agrees B beforehand, do they?
So B is just set in the beginning of times, and it stays always the same. And it can be optimized. So think of B as something that is large enough so that if your noise looks like this, then most of the time it's going to be inside of this B. And this is something that can be adjusted.
Do you need most or better than 1?
Sorry?
Do you need most? Or do you need more than something like 1/2?
Yeah, we need this to be large enough. Yeah, our analysis is not super optimized. So yeah, that's something that I'm actually curious. It's a constant. It's a constant that you just set. It's a constant that you just set in the beginning.
So when you return to normal mode, the initial value of CI is what again? Some small value? Or?
Yeah. So initially, we start. So how do we start? So x1 is A times x naught plus u naught plus v. So we assume that we know something. We know the density maybe of this, or the distribution. So we assume that they live somewhere. So yeah, we start somewhere. Okay, so actually I don't have time, of course, to go into analysis, so I just want to say a few words, it's probabilistic analysis. What we do, we analyze the result of each round, so each variable length round. And the goal here is to show that after a round is completed, this beta's moment tends to decrease compared to the start of the round. And what we need this boundedness of alpha moment of Vi to show that the probability that the emergency lasts as long as J is decays something like this. That's here we use the fact that we exponentially increase this interval. So this interval that we test for. And yeah, and then there are quite a few hoops we need to jump through. So xi, so this value is not a martingale. So it's kind of tricky to analyze directly, but so what we do, we craft a majorizing sequence that is a martingale, and then we use this bound on this probability of that emergency lasts as long as J to bound the conditional expectation of this majorizing martingale. This very high level overview. Okay, so I just want to say that it extends in various directions. So finer quantization is a very straightforward extension. So here really everything works the same way, and we use the actually uniform scalar quantizer just with the different number of levels. It also generalizes for correlated noise. As long as the noise covariance matrix has a bounded spectrum and it's Gaussian, then the analysis goes through. And higher dimension as well. So for high dimension, this M star is still given by this, and A now is given by this formula where lambda M is the mth eigenvalue of A. And I guess I need to stop here. And maybe let me just say this, that we also, so today I mostly talked about, actually I only talked about this, but we also have results on this entire curve, so the bounds on this entire curve, especially the lower bound that works for very generally, and we have an upper bound that works for variable rate quantization. So one of the I think exciting open problems here is to see to have an achievability result which tells us something about this entire curve for this scenario that I talked about, the fixed rate quantization, where you only send, say, one bit. So can we say something about this entire curve? And the bounds that we have right now are a bit too weak for that, but experiments suggest that actually the lower bound that we have is pretty tight. So experimentally, we tried running Lloyd-Marx quantizer, and the lower bound is very close to that. So an analysis would be interesting on that case. I'll stop here. Sure.
You talked about the adaptive zoom-in. You attributed it to somebody, right, before you started on the detail?
Yeah. I mean, so this zoom-in, zoom-out idea, it's been around.
So
yes.
What's the novelty compared to what was known?
So the novelty is the analysis. So first, it's not the same. It's not this. I guess the idea itself that you need to zoom out, and you need to, if the system is far from what you conjecture it is, so that has been around. But so this particular strategy that K steps and then you test, so that is new, as well as with the analysis. The fact that it actually achieves the optimum.
What was the known result? So the early result didn't have a precise estimate on the number of...
On the number of, so the M star. So what we wanted to have an answer about what this M star is. Yeah. So but the ideas of zooming in, zooming out have been around.
Another question actually is related to the question that was asked earlier. So everything seems to involve the knowledge of A.
Yes.
So let's say that you overestimate A, right?
Uh-huh.
So somehow intuitively you're trying to control a system that's potentially even more unstable
right.
than the one you're dealing with.
Right.
Do you have a guarantee that your scheme will work if you use the wrong A?
Oh,
I think that was related to the question that was asked earlier.
Oh yeah, so if A is larger than you...
A that's larger than the true one, will it work?
Yeah, I think if you use A that is larger, it's gonna work actually. Yeah. It's. I mean, all the analysis. It's. Yeah. It works. If the other direction is not gonna work. Sure.